Good morning, we're Mia and Ryan, and this is our fluid mechanics project on Bernoulli's timer. Our inspiration for this project comes from the ancient Persian fenjon, a water clock that consists of a bowl with a small hole in the bottom. As water flows into the bowl sinks at a constant rate, allowing farmers to measure time and evenly irrigate their fields. We've taken this concept and adapted it into a 3D printed cylinder, using fluid mechanics principles such as Archimedes' principle of buoyancy and Bernoulli's equation to predict how quickly it will sink when placed in water. To start, we developed a predictive model using MATLAB. This model takes into account the physical characteristics of a cylinder, such as its height and the diameter of the hole at the bottom, etc., to estimate how long it will take to sink in water. Once we had the model, we 3D printed several cylinders with holes of different sizes. Then we tested each cylinder by timing how long it takes to sink when placed in water. The goal is to compare our experimental results with the predictions from our model.
On to the math. This is the model that we used to define our variables. You can pause the video here if you want to keep track of all of them, but the most important one that we'll need for now is little h of t, which is going to be the height of the water inside the cylinder above the base of the cylinder. So next we need to apply Bernoulli's equation to find how quickly the water is entering the cylinder, which you can see doing here. And then the next thing we need to do is use algebra and the Archimedes principle and conservation of mass to find all of the unknowns in terms of little h of t. That way we have a constant variable that we can use for integration later. And this, at the bottom, you can see our big, ugly differential equation, which we will integrate later using computational techniques. Here's the cutoff h of t. It's basically the h of t where it's the height of the water at which the cylinder will sink. And we need to use that to find the t at which the cylinder sinks. So we calculate that using a Runge-Kutta scheme, which you can see here. Basically, what this does is it iterates through instead of to very closely approximate the integral instead of actually solving it analytically, which isn't possible. So you input the physical characteristics of your cylinder at the top, run the script, and the t-value at the end will be how long it takes to sink.
Okay, now let's talk about the results. As we expected, larger holes lead to faster sinking. However, the experimental data is somewhat off from our predictions. This discrepancy can likely be attributed to the viscous effects of water. Our model was based on Bernoulli's equation, which assumes perfect flow conditions, such as constant velocity profiles and no turbulence. In reality, water's viscosity causes deviations from these ideal conditions, which explains why the sinking times are different from the predictions.
Reason number 2 is probably drag on the cylinder as it sinks. Imagine you throw an object into a pool. It'll sink much slower than if you just threw that object onto the ground, and that is due to the drag force of the water on that object. We did not account for this drag force at all in our model, and that's reflected in our results because the bigger the hole, the faster the cylinder sinks. And the faster the cylinder sinks, the more drag force is acting on it. And since we didn't account for drag force, the more drag force is acting on it, the more wrong we are. If we'd had more time, we could have had more data points, more cylinders. The reason we didn't is because they needed full density on the printer, and they took about 6.5 hours each. And we'd look into calculating drag and viscous effects, possibly using the Navier-Stokes equations. Thank you for your time.